We're gonna go through the tutorial, and for those of you who are new to PyHF, this will be kind of a warm refresher, warm introduction to sort of what PyHF is, what it does. For those of you who are somewhat more experienced or have used to fair analysis, think of it like a review and maybe learn something you didn't before. This won't be a very complete tutorial. This is just a very light introduction to get people kind of warmed up. Feel free to grab snacks in the middle of it, but you're just mostly going to be following along with me as I go through this tutorial on my computer in this notebook. So you can see this web page of what the tutorial looks like. We have this introduction here. We have a video from Matthew at the SciPy conference back in 2020, giving sort of a verbal overview of that with some slides. We also include explanations on how to do installation of PyHF for this particular tutorial. You can do this locally. If you have access to Alex Plus, you can install this on Alex Plus. You can also do this in your browser as well, and also explains how to install any additional extras such as using TensorFlow or PyTorch or Drax. And then, of course, as we always want to remind people, you should feel free to use PyHF citation, and we provide a little command line utility here, which will also show spits out the current citation for whatever version you're actually using for your work. So with that, we're going to go ahead to the introduction, and this is about HIS factory models. And so the idea behind pyhf is that it's a Pythonic interface for HIS factory, hence the name pyhf. And so for us to get started there, we would generally have to explain what HIS factory models are. We're not going to go into a very pedagogical overview of what they are. That's something we cover in the tutorial, which you can go through on your own time. But what we talk about here are what we call HEP-like models. And HEP-like on some level means that you have some sort of signal that you're searching for, some sort of background, such as your standard model background as your hypothesis, and some sort of observations recorded from your detection. And the idea behind that is you have your signal, you have your background as an observation, and you want to make a hypothesis test saying how whether your data is more compatible with your signal plus background compared to your background only model. That's the fundamental hypothesis testing that we do in particle physics, and that is what HIS factory was designed for. So what you can see here in this code, we're just gonna go ahead and import some stuff. We're gonna import JSON, matplotlib, NumPy, pyhf, and the Brazil plot, which we'll explain in a second. Is this big enough for everybody in the room to see? Okay, I can make it just one more step bigger. Maybe that's a little better.
Can you also mention that they can follow along on the binder hub?
Yes, you can also do this on your binder hub using the SSR that Matthew just mentioned as well.
If you scroll to the top. You can,
on this one? Oh, you mean in the other page, right?
Yeah. If you go to the intro to HIS factory.
Right. So if you click on the top, you see this little rocket icon here. This rocket icon will let you, if you click on the binder, will open it up on Binder, and you can also open this up on Google Colab as well. So there's plenty of online resources available for you to use. So it's not just on your computer, and particularly if you have a Windows machine where yes, PyHF can kind of work on Windows, but we don't actively support it to some extent.
Not yet. In the last release, it kind of works. But
all right, so we've imported this. So we're going to start with a simple model here that we call a simple HEP-like model. So I'm just going to go ahead and highlight this box just to give you what we mean here. So this particular model, we're looking at a histogram of 2 bins. And each of these, we're going to have a signal histogram, a background histogram, and a background uncertainty for each of those bins. The signal histogram has 2 bins with 5 counts in the first bin, 10 counts in the second bin. The background is going to have 50 counts in the first bin and 60 counts in the second bin. And then we put an absolute uncertainty of plus or minus 5 events in the first bin and plus or minus 12 events in the second bin. You could calculate this uncertainty here yourself. That's a 10% background uncertainty in the first bin and a 20% uncertainty in the second bin. So we're going to go ahead and create that model. And this is what you should see. This is a pyhf model. And so we can go ahead and dump information about what this model actually looks like. And this is the JSON specification. This is the JSON HIS factory specification for the PyHF model that we just created. You're going to see here a list of channels. We're going to have a single channel here called aptly single channel. This single channel is going to have two samples. It's going to have a signal sample here and a background sample here. In each of the signal samples and background samples, we have the data, the expected event rates from the model, from the signal model and from the background model that we just talked about for the bins. And then each of these samples also has what we call modifiers. Modifiers is a term that we use in PyHF. This is roughly equivalent to what you might call systematics and Newton parameters. Also, the terminology gets a little bit lazy in particle physics, so we've tried our best to kind of clarify what these are by giving it a slightly different name that more represents what the actual functionality of this. So, for example, on the signal model, let's go with the background model first. The background model, we put in a background uncertainty on this using a shape systematic modifier. And this modifies the expected event rate of the background using the data of this modifier, the 5 and 12 that I just mentioned here. That's what we mean by modifier. It literally is modifying the background model here as we vary the parameters of the shape systematic. Similarly, we also have one for the signal called mu. This is a normalization factor. This is also indicated as a parameter of interest. And a parameter of interest is something where we fit the model and we care about finding the value of this parameter of interest that maximizes the likelihood, or we set the parameter of interest to a fixed or known value to perform a hypothesis test according to the CLS methods that we'll explain. But this is what the JSON representation of this model looks like. Again, this very simple example is a little contrived, but it's simple and it's meant to show you that it's declarative and describes everything in slightly human readable language, but it's computer readable. Do we have any questions on this before we move on? Everybody seems okay with this. All right. So from the specification, we can go ahead and print lots of information about this. You can ask for the model channels, the number of bins in each channel, the samples, the modifiers, the parameters, the auxiliary data. So you can see here we have one channel called single channel. Single channel has 2 bins. We have 2 samples, background and signal. These are the modifiers here and the type of modifier. We have mu as a normalization factor and uncore background uncertainty as a shape systematic. And then we have 2 additional bins of auxiliary data. We can talk about auxiliary data in the next section very briefly. But one thing that I want to point out here is the reason why we expose channels and samples and modifiers is that PyHF builds in the back end or sort of under the hood a very large 2 or 3 or 4 dimensional tensor of just all these numbers, and it's just doing matrix calculations under the hood. The order of the elements in these matrix is important, and we record the order of the channels being used, the order of the samples being used, the order of the modifiers being used. So you have access to this order if you need to look into the internals of what we're doing and extract some information that we don't necessarily give you from the API. Most of the information is generally accessible, but expert users such as Alex, who works on cabinetry, would need to know what the order of these parameters are to be able to extract some certain information specifically. But that's why we allow this information to be exposed. All right, so this last piece here is this auxiliary data. These numbers are a little bit different, and auxiliary data is something that comes with HIS factory. And so before we explain what that is, I want to show you what the HIS factory definition looks like here. Now, the HIS factory definition, most of what we talked about so far with the samples, with the channels, with the modifiers, kind of went into the first place zone that you see here on the left-hand side. However, we have an additional term in HIS factory called the constraint model. And the constraint model is controlled by what we call auxiliary data. In the main point zone that you see here on the left-hand side, this N subscript CB is the observed data or any data that you feed into the model The auxiliary data goes into this A sub chi term that you see here on the right-hand side. Now, unlike the data and sub CB, which you give to the model, the auxiliary data is completely determined by the model specification. It's not something you need to provide. When you define the model, we're able to calculate the auxiliary data for you and provide it for you easily. You could do this yourself, but this is part of what pyhf is meant to be used for, to calculate some of the common things that you don't need to calculate yourself. So this auxiliary data here, if we go to the pyhf documentation, which I'm going to go ahead and just quickly show you for a quick second. In the pyhf documentation, in the introduction for this, we have a very nice table here. And this very nice table gives you, I'll make this big enough for people to see. This table here gives you all the different modifiers along with the associated constraint terms for the test factory model. Now, the one that we care about is going to be the shape systematic, and the shape systematic is going to have a constraint term, which you see here, this sort of Poisson that you see here on the right-hand side. And so we need to calculate the auxiliary data for this constraint term. Let me hide that. Hard floating mini controls. Okay, so if we go back here, the constraint term for the auxiliary data for the shape systematic is constrained by Poisson. We need to calculate A sub chi for this. And this is the value that you see here in the bottom equation. So we're going to go ahead and calculate this for you manually. And of course, you can see this table screenshot in this notebook. But I just wanted to show you that this is all in our online documentation. We tried to do a good job of maintaining very good documentation because all of us, Matthew, Lucas, myself, we were all, grad students and postdoc, and now one of us is at least a professor, and we all struggle with statistics on some level. And a lot of it was something that we just had to learn by talking to people. And then when we learned that, we wanted to document this in a central place that was more accessible and sort of readable instead of just math alone. We do supplement this with math where we can, but we try to explain this in a way that gives you slightly more intuition. Do you want to say anything or? All right. So if you look at this first row here, we have this constraint term, and this constraint term is 1 over sigma b squared. So we're going to go ahead and calculate this. So if you remember, the background uncertainty was 5 events and 12 events. We're going to divide that by the 50 and the 60 for the number of background events. And if we do the square, we're going to get the auxiliary data 125. pyhf just does this for you automatically, so you don't have to look up what those formulas are or figure out what the constraint terms are and do this. And you can evaluate the aux data and confirm for yourself that this matches. But this is a nice way where if you are trying to teach statistics and you want to teach this factory, this is a nice pedagogical tool where you can have the students do this themselves and then confirm with what pyhf gives you. So it's a quick way to do sort of a validation check or a gut check. So that's the auxiliary data. Now we've talked about the auxiliary data. Let's go back to what the model tells us about the expected data. Whoops. So you can see here that it didn't work. And this didn't work because, and I always catch myself, always. I really should remind myself. But you should see this error here. Model.expected data requires parameters, pars. What do you call this pars in pyhf? But this is parameters. And you might be wondering why this happens. Let me scroll up very quickly back to this equation you see here. This equation you see here, we have this sort of theta term which describes all the different parameters. We don't give you by default, there is a default set of values for all the different nuisance parameters, but you need to specify the nuisance parameters in order for us to give you the value of lambda. This lambda that you see here, the expected event rate, is the expected data of the model, but lambda depends on theta, the parameters. You need to be specifying theta in order to evaluate expected data. So we're going to go ahead and specify the default for mu and for gamma, the shape systematic. The default parameter for both of those is 1. I'm gonna go ahead and pass this a 1, but also remember that the shape systematic is not a single nuisance parameter, but 2 nuisance parameters. So this is why I have to pass in 3 parameters here. And if I evaluate this gives me 55, 70, and the auxiliary data. The 55 and the 70 you get because that is the signal plus the background. Remember, the normalization factor on the signal scales the signal by some multiplicative modifier. The signal that we used here was 5 and 10 for the first 2 bits. So if we have a mu of 1, then that means it's going to be just 5 and 10 added to the background. If I change mu here to 2, where I do 10 and 20, you can see that this changes a little bit by that amount. I might say, well, this is confusing for me to include the auxiliary data. You might run just the actual data and not just the auxiliary data. You could do expected data and pass it, include aux data equals false, and just get only the actual data from the model and not the auxiliary data of the constrained model. But you can also ask for the model actual data and the model aux data separately as well. We give you all these APIs to allow you to pass with it. Data is kind of an overloaded term. For us, data means the observation, but also means the expected actual data and the expected auxiliary data, as well as the expected data. So we try to give you additional API to be clearer about what you mean to grab out of PyHF from these models. Now, the next thing I'll mention is this parameter ordering. I mentioned under the hood, we do everything through this sort of giant matrix here. The parameter ordering is important. And you can ask the model for the order of the parameters we use to fill in this matrix. And this ordering typically is going to be alphabetical, but don't just alphabetically sort it yourself. Rely on what PyHF gives you for the ordering because we will always be self-consistent. At the end of the day, you can serialize his factory in a JSON file. And if you load this up on somebody else's machine, PyHF is going to be consistent about the ordering with respect to your own machine, but not across machine. So try to rely on what PyHF gives you for the ordering, and everything will work out. Now, not necessarily we give you the parameters and the modifiers, but that might not necessarily be the order of the parameters we use in the model. That's why there's an additional term called par order. Again, this is something that we will try to harmonize in the future with PyHF and make this less non-intuitive. But for right now, there's a bit of a separation of concerns here. But we try to clean this up as we move forward and we get feedback from users who use this, especially expert users who care more about this kind of ordering. For your everyday work, you typically will not need to care about this. All right, now if you look here, you see these parameters are just parameters. But as I mentioned before, if you look back at the top, you might not have known that we needed to specify 3 nuisance parameters and not just 2. We only have 2 modifiers in this model that we're talking about, but one of those modifiers is controlled by 2 nuisance parameters. If we go ahead and spit out the model config parameters down here, you can see that for the first channel and the only channel we have 2 bins. But if I look at the uncorrelated background on the background sample here is a parameter constrained by praise zone, which you see in this sort of printout here. And I can print out the number of parameters on it, and it will tell me that this particular modifier constrained by praise zone is controlled by 2 nuisance parameters, 1 for each thing. And that's how I get this information out of PyHF in a programmatic way. PyHF will have all of this information for you accessible in a way that you can program against. So you don't have to remember any of this. It's built into his factory and we get this for you. The next thing is you wonder, how do you know what the defaults of these nuisance parameters are? We get this for you. So you can ask PyHF what the suggested initialization should be. This is something you can control with the factory model. It's something you can define as part of your model specification, as part of the workspace specification. But if you don't specify, we'll give you some sensible defaults so you can start working with those defaults. We also give you some default bounds as well for each of the parameters in the model. And we also give you whether or not those parameters should be fixed in the model. Sometimes they need to be fixed by default, sometimes not. We give you all of this information through the suggested API of the model config. So for all of this, we could have, instead of manually specifying 111 to figure out the model expected data, we can get the initial parameters and then evaluate the model expected actual data at the initial parameters. And then, of course, instead of me knowing where the parameter of interest is in the number of parameters I have, I can ask the model for the index of the parameter of interest and then change that. So in this example, let's say I wanted to get the expected actual data before the background only model. The background only model here is when I set the normalization factor and the signal to 0. I don't know what that is. So what I can do is copy the initial parameters and then set the parameter of interest to 0 in the back parameters, and then reevaluate the expected actual data, not just get the background only expectation. I'm going to stop here if anybody has any questions first before moving on. Alex has a question in the room.
A bit technical. This copy here is not needed in principle, is it? You don't touch, because you can't touch the internal init data stuff, I believe. Just asking to make sure I don't accidentally introduce any bugs.
It's a good question. We could just check this right now. So init parse.
Well, I think the reason why we do this is because like we're here setting this to 0. Like, but then we wanted to be able to show that you had the original model config and then this like alternative one and have them both available for you in the notebook.
You just want to track
a
different name.
Yeah, exactly. Okay. So it's just kind of making it syntactically sugary nice, so you don't have to change the model POI back later. But
yeah, what I wanted to make sure is that what John tested, that we don't override anything, which would surprise me. Okay.
Yeah, cabinetry is doing everything right.
Yeah, I think this is the one thing that's maybe a little frustrating with Python when you have mutability. That's sometimes never clear if something you change might mutate the underlying thing. But we've tried to be you're right. We've tried to be a little bit better about this to prevent users from accidentally screwing something up.
I think it works very well overall. I think it's hard to mutate something by accident.
Yeah, you have to kind of dig down into the API to get there. So,
any other questions? If you have questions, I assume just pipe in. But yeah, we have one.
Yeah, it's Volker. I have a question on the suggested init and the suggested fixed. Can you explain a bit what does pyhf do there? Because it sounds a bit like black magic to me.
In terms of how it does it?
Yeah, like how does it know that a parameter should be fixed?
So there are two ways. By default, none of the parameters are fixed. In the workspace specification, you can define a parameter to be fixed as part of the configuration block in the workspace. And that is more, we'll talk about that in a second. We'll show you what a workspace looks like. But workspaces is a combination of the model, which is all we've been showing you, the observed data, and what we call a measurements block. That's the Hispactory jargon for. And a measurements block contains configuration for a particular measurement, such as if you want to change the default init value from 1 for the normalization factor to 10 instead because you have a larger range, or you say that some of the nuisance parameters, such as for your luminosity, get fixed by default, then you can set that. pyhf will load that up, but if it doesn't see any configuration for the parameter, it will load up what the default should be for that particular modifier. If that makes sense. Maybe it is a little bit magic, but hopefully not as magic as you were thinking. We tried to combine the configuration from the workspace with the default configuration, and the workspace will override any default built in.
Thanks.
I think we try and give kind of like dumb defaults as well, so that we don't try and do anything clever, so that you know, it something might run, but we're kind of wanting to try and push responsibility to the user.
Yeah, immediately, this is why it's nice to have someone like Lucas on our team, because Matthew and I, we tend to like magic quite a lot more, but what you do?
I don't know about that.
Oh, okay. Well, but Lucas always tends to warn me at least that we shouldn't make things too magical, because you don't want to become too much of a black box here. We try to make this as friendly as possible, but not put too much on top of it. Because at the end of the day, you have somebody like Cabinetry who comes along to add more features on top. The pie chart becomes bare bones. Alex?
Yeah, one thing to add about exactly this. Here, the init is effectively an init for the minimization. And ideally, it doesn't matter what you set there, right? Like ideally, you still converge. Now, in Cabinetry, for example, this init also will be the default value for the parameter when creating an Asimov data set. Because for free floating parameters, you have a choice of what to set them to. Like the data set is still Asimov, so you need to make that choice. So at that point, the init that is set in pyhf has like this double role. So you can attach extra meaning to that, but that depends then, of course, on how you're using it. That is a choice that like is made there.
Yeah, okay. Thanks.
Any other questions, comments, complaints? Okay. Hopefully people on Zoom have been able to hear all the questions, right?
We'll take silence as yes, so.
Okay. I mean, I'm sure they'll pipe up if they start not being able to hear us. All right, so now we get on to, this is a nice segue, now we get on teachers doing inference. Now, the idea behind pyhf, you build all this model, you're building a PDF. And this PDF allows you to do statistical inference on it. It is a likelihood function. And you can see here that we're able to evaluate this likelihood as a function of the parameters we pass in. And so what we're going to go ahead and we're going to do this for both the background only model and the signal plus background model here. So the first thing we're going to do is just make up some arbitrary observed data from our fake detector. And the observed data that we have here is going to be 53 and 65. And we're going to go ahead and add this to the model config auxiliary data. I will note this is a common pattern because you're combining the observed data with the auxiliary data. That's something you always do. And we're going to go ahead and evaluate the log PDF of this model for the background only model for the given data that we just passed in. And then we can also do this for the signal plus background model. And you can compare some slight difference that oh, sorry. Let me fix that. That should be different. There we go. And so what we're doing here is the observations is going to be the sort of X that you see in the equation up there. And then the parameters is going to be the theta. And what we're doing is we're evaluating for a given set of observations, whether the background only model or the signal plus background only model is more compatible with the observations that we passed in. And you compare the log likelihood of these two, and the idea here is to minimize that value. And in this case, we're not necessarily performing inference yet. Inference implies some sort of minimization or actual iteration to find the maximum log estimators. Actual do a fit for that. We're just calling the log PDF function, but a minimizer will call log PDF thousands of times, hundreds of times, in order to find the set of parameters for the model that minimizes the likelihood or maximizes the negative log likelihood. Other way around, I think. Yes. It's the negatives always throw me off. We're finding the set of parameters that minimizes the negative log likelihood to find the maximum likelihood.
Yeah.
So let's just go ahead and do an inference. Let's just fit this. We'll do an unconstrained fit. Nothing is fixed in this model, and we're just going to figure out what it gives us. And what you can see here, this is the output of the MLE fit. Of course, feel free to get snacks. So what you can see here, and this output gives you three values. The output of a fitting procedure gives you the values of the nuisance parameter that maximizes the log likelihood that you're seeing here. So in this case, we can read this out. We get mu hat is about 0.54 and gamma hat is about 1. So that means approximately the value of mu that maximizes this is 0.54. And the shape systematic, we don't really need to change at all. Those can be at their default values of 1. And that's it. That's all we have to do, and we've done statistical inference in particle physics with this model. All right, so now we're going to go ahead to hypothesis testing. So hypothesis testing is of our ability to either reject a standard model hypothesis or reject a beyond the standard model hypothesis, meaning we can either reject the background only model or reject the signal plus background only model. Sorry, reject the signal plus background model. And the difference between those two changes whether the test statistic we use for that hypothesis test, but also we change what our H null and H1 are, our null and hypothesis, our null and alternative hypotheses will change depending on the question we're trying to ask. And we evaluate this using in particle physics what we call the CLS method. And the CLS method here is a modified p-value, which is a ratio of two different CL values here. The CL of the signal plus background compared to the CL of the background only. And there's some math here. We can get an idea that the CLS plus B is evaluated from the null hypothesis, while the CLB is evaluated from the alternative hypothesis. And this, in the case that we're trying to do a fit or a hypothesis test where we want to exclude the background only model in favor of some alternative signal. So I'm just going to scroll down a little bit in the interest of time, just to show you how hypothesis testing works. PyHF gives you a API called hypotest, which is short term for hypothesis test. And this is under the infer submodule here. If you scroll up a little bit, you can see infer has a maximum likelihood estimator fit. And under the same infer submodule, we also have hypotest. We specify here the value of mu that we would like to, the value of the parameter of interest that we like to evaluate this hypothesis testing for. We pass in the observed data, the 5365 plus the auxiliary data, the model, and the test statistic. And if we just go ahead and run this block of code, we're gonna get some error, some warnings here. In this case, PyHF told us that, we're using a test statistic of Q, but the parameter of interest is bounded below a 0. So perhaps it's better for us to use Q mu tilde instead. So we can go ahead and change that as well. We evaluate this because you can see here, the parameter of interest is bounded below a 0. So we're going to go ahead and change the test statistic to Q mu tilde. And we can just go ahead and rerun this. There's no more warnings anymore. And we get the CLS value for the observed CLS, as well as the expected band for plus or minus 2 sigma, plus or minus 1 sigma, and the central value of the CLS. And this all comes for you relatively easily out of PyHF. This will be a lot more work because under the hood, the hypothesis testing is running something like 5 or 6 different fits for you. It's not a single fit, but it's 5 or 6 fits. There's going to be a fit for the Asimov data set, as Alex was bringing up before, but there's also going to be a fit for the background only hypothesis and the signal plus background. And we do some comparison to compute the test statistic and give you the CLS value for everything. And we do this all for you. Now, armed with all of this, we can also compute what we call an upper limit. And an upper limit is typically something where we do a discovery fit to give us a sense of what the upper limit of the observed or expected cross-section is for some sort of model. And what that means is what the sort of maximum cross-section should be for us to be able to exclude the signal model at some particular point, or maybe sort of the minimum limit where beyond that limit, we are not able to statistically say anything about that signal model anymore compared to the background. Perhaps because at that limit, the background and the signal become too alike, and it's hard for us to differentiate between the two. And of course, we have an interface for this, and you can see this interface here. This is all the documentation, but yeah.
I have a question here. In the parameter of interest values, can you go above 10 in the upper limit of the range?
You can. So in this case, what you can do here, if we have this bounds, we can go ahead and do like say my bounds like this. And then to my bounds model.config.py index equals 20. I cannot type today. All right, we can do this, and then we can go ahead and do pi bounds equals my bounds. And this will allow us to change the bounds to that.
I should note though that in general, we wouldn't super recommend that because we would actually suggest that if you need to scale, if you actually need to scale up well beyond 10, that maybe the model that you're choosing, you might want to consider editing your model a little bit. So it is possible to do, but like unlike ROOFIT, we're kind of making the assumption that you've already started from a reasonable model and you've done some model building ahead of time or model consideration. And so ROOFIT will let you basically put huge bounds on things and it will do its best to try and figure it out. But we're kind of assuming you've done a bit more work ahead of time. So if you put the upper bounds as to 100 or something, and you actually need to scan all the way up to 100, the fit might fail. So it's totally fine to do what Giordon just did, but if you put some huge upper bounds on your POI and that fails, then you might want to consider changing the model you're using.
Yeah, I understand. It's just that sometimes depending on the parameter value of your model, like let's say the mass of a new particle, you might expect a really tiny signal or a really huge signal, and that's what I was wondering.
Yeah, totally reasonable. So
all right, let me just quickly trace that. By the way, I type fast, so you don't have to try to keep up. All right, so with the upper limit, we're gonna go ahead and quickly evaluate the upper limit here. As I mentioned, and the upper limit is related to the upper limit of the parameter of interest, where we can say, it's sort of the limit on where we can say something statistically significant about the model. Beyond that point, we cannot say anything anymore, meaning that's sort of like the maximal value or sort of for the cross section of the model. In this case, we get an observed upper limit of 2.5 and an expected upper limit of 2.1 on mu. But we can go ahead and create what we call a Brazil band, which is relatively common, and make that plot where we evaluate this for a bunch of different parameters of interest values and make this plot. And you can go ahead and see where this red line intersects the expected line, the dashed expected line here. It's about 2.1 for the expected and about 2.4 for the observed. And the upper limit is where these lines intersect with CLS equals 0.05. It's the 95% limit there. And pyhf makes this all easy to do. And in fact, if you wanted to do all of this and do, for example, a hypothesis test across all the different parameters of interest values, you can calculate the upper limit yourself and do the manual interpolation as we're showing you there. There's lots of different ways to skin a cat or skin a model in this case, and it's going to be up to your preference on how to do this. We try to make it as easy or as hard as you like. All right, with the sort of last 8 minutes or so, let me just quickly check if I want to do. Yes, we have enough time. So as I mentioned with your question before about the suggested init and suggested fix, we're gonna go ahead and look at the workspace. So as a reminder, this model here just has channels and nothing else. It's just the model specification, sort of the structure of the channels in the model and nothing else. However, I'm gonna go ahead and load up data that we have in here and load up the workspace. And we're gonna go ahead and dump this. This is the same workspace. It contains the same model specification, but has some additional information that we loaded towards the bottom here. And I'm just gonna show you. You're gonna see key here for observations, where we specify the observations for each channel, the sort of data that we've recorded from a detector or from an experiment. But it also has this measurements object here, where we can specify configuration on the individual parameters as well, and that can be recorded in the workspace. And this is a version 1.0 his factory JSON workspace. This is something that pyhf also gives you, where we built pyhf not only as a Python library, we also came up with a his factory JSON schema to be able to define the his factory models in a JSON format. And of course, you can ask the workspace for its measurement. And you can also get measurements by the name as well, or by the index of the measurement, because you can have multiple measurements in a workspace. But we can ask for the model from the workspace, and that's going to be the same model that we were talking about before. And you can also get data for that given model here, because perhaps the model doesn't have all of the channels, or maybe some of the channels are missing, or has a different order, and we give you the data, including the observations for free. So you can see, you don't have to build up your data manually. If you define a workspace, we give you some sort of syntactic sugar to make this easier to access as well. Yeah. And then, of course, we can also ask for the data, not including the auxiliary data as well. And so at all different levels, whether it's at the model level or the workspace level, we give you some of the same interface to access all of the same information. And so that's it for models and workspaces. And I think at this point, there is one workspace left, but honestly, we're not going to talk about it too much. I think at this point, I've done a lot of talking and given you kind of a warm overview of what pyhf is, how it works, and then there's a lot more complexity we can add there. So from this point, we'll open the floor for questions, comments, and anything else before we move on to the rest of the day.
All right, thanks very much, Jordan. So we'll go ahead and go to Zoom first. So if you are on Zoom and you have a question or a comment, please raise your hand. Okay, so scrolling around, I don't see any hands raised yet, so we can go to the room next. Volker?
I have a question on the measurements. Can you just explain what what's the purpose of having several measurements? Is that for fitting several parameters of interest? Or?
There are a lot of different purposes. From my perspective, I tend to only ever have one measurement object. But for measurement, you could say have different measurements that have different default configurations for some of the parameters. Maybe you have one measurement that fixes some subset of parameters, and then you use that measurement to say, let's fix the nuisance parameters for flavor tagging if you're doing something in Atlas or CMS or Atlas should be, and you fix the nuisance parameters for flavor tagging and need to fit there. But then another measurement could be to leave them unfixed. And those measurements just, for me, have a different set of default configs. Beyond that, I don't think there's a utility. I don't know, Alex, is there any other utility for measurement beyond that?
I think, I mean, if you have lots of interpretations of your signal, you could plug them all into one workspace and just put them into different measurements. But, I mean, you mentioned this essentially, so yeah. I personally don't use that feature either, so I can't say much.
It's something that's built in his factory, but you are right, that came up with the other thing. This is a little feature that you could use. Imagine you have the same background model, but 3 different signal that goes on top of it. You could either make 3 separate workspaces, and each of those workspaces is signal plus background, but with a different signal with the same background, and it's 3 separate files. You could also make what we provide a background only workspace and then patch that for each of the signal model. The other thing you could have also done is have all of those signals in the same workspace and have 3 different measurements that fixes the normalization factor for each signal to 0. Branches?
Yeah, I'm wondering which of these is most performant, if we know. Maybe that's a good question to imply, which of these implementations it's the most performant to do.
Performative in terms of like calculations
Yeah,
or something
like
else?
because I need to do some patching, or I need to do fixing and calculation, or I need to run a workspace without doing any of these things. So I'm wondering if one or the other implementation is more performant. That's one comment. And the third option you mentioned, I'm gonna talk about this later. At the end, I'm skeptical if it's not very clean implementation, because you end up with a workspace with a lot of samples, a lot of normalization factors. So not very clean.
Yeah.
It's not problematic, but that's my comment on this.
Yeah, I think the short answer is like in terms, I mean, I wouldn't worry in general too much about the performance, but I mean, in terms of like, if you're just trying to compare having things already be defined versus just applying a patch, like, because those operations are usually very small, but I mean, having it already be defined is, I guess, probably more performant. But I agree with you that I think it's from a user design perspective, probably better to work with like the patch sets, because it can kind of it nicely separates things out. So
Yeah, I say on some levels, all the configuration, Alex.
Yeah, I think for performance, probably turning off signals is slightly worse for fitting, I think, because you still have those in the model.
Yeah.
So you still have longer tensors. And I think that probably is going to be slightly worse for performance. I don't think it will really matter unless you have like 1 billion signals.
yeah.
But technically, I'm assuming that's a bit worse.
Okay. Yeah.
Actually, there is a slight configuration difference. In the first 2 options where you maintain 3 individual workspaces or your background plus your signal, in those cases, you will have to sort of recompile the model if you're trying to do differentiation. But in the last case, however, because that model contains everything all at once for all the samples, there's no recompilation happening for all the differentiability. But I believe on some level that becomes more of a niche or expert user, and that's maybe something where you have to leave, but.
Yeah.